the dot product of vector A and B cross C denoted by A dot B cross C. This is called as scalar triple product. From the property of scalar triple product, when the two vectors are same inside the scalar product, the value is 0. If the three vectors are coplanar, their scalar triple product is 0. That is A dot B cross C is equal to 0. Hello everyone, a warm welcome to one and all. This is Yashruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study a scalar triple product. So what do you mean by this scalar triple product? Now, consider three vectors, vector A, vector B and vector C. So there are three vectors, vector A, vector B, vector C. Then the dot product of vector A and B cross C. So that is the dot product of vector A and B cross C denoted by A dot B cross C. This is called as scalar triple product. And A dot B cross C is also denoted in the form of a square braces like vector A, comma vector B, vector C. So vector A, vector B, vector C inside the square braces is nothing but the scalar triple product of three vectors, which is nothing but vector A dot B cross C. Now, scalar triple product is also called as the box product. Now, let's see what are the observations we need to study under the scalar triple product. So, scalar triple product is always a scalar quantity. So, the value you will get is only in the numerical form and hence it is a scalar quantity. Suppose I express all the component form, let vector A be A1i, A2j, A3k, vector B be B1i, B2j, B3k and C be C1i, C2, C3k. Then the dot product of vector A and B cross C, or we can say the scalar product A dot B cross C is nothing but the determinant of vector A component, vector B component, vector C component. So that is all the components A1, A2, A3, B1, B2, B3, C1, C2, C3 in the form of a determinant. This is how we are going to evaluate vector A dot B cross C. And in scalar triple product, the dot as well as the cross can be interchanged. For instance, if I write A dot B cross C, then I can write it as A cross B dot C. So, we can interchange the dot and cross product. The value is one and the same. Next, A dot B cross C or cyclically arranged in box product. So, we know that A dot B cross C can be denoted using A comma B comma C. This is same as B comma C comma A and this is same as C comma A comma B. Because why? We know A comma B comma C means it's a determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. So, when you need two rows or two columns or interchange, suppose if I interchange these two, then it will be B1, B2, B3 in first row, A1, A2, A3 in the second row. If any two rows or any two columns are interchanged, the determinant value is one and the same. So, therefore, ABC is same as BCA and it is same as CAB. Now, in scalar triple product, if two vectors are same, when I am taking the scalar triple product of the two vectors which are same, for instance, we can say A dot B cross C, then the product is 0. If any one vector is one and the same, for example, if I have B as A only, that is vector A cross C, then it is 0. So, if vector B is equal to vector A, if the two vectors are same here, then the scalar triple product is 0. Or C may be A sometimes. For example, vector A dot B cross A. This is also 0. So, therefore, if two vectors are same in the scalar triple product, the value is 0. And from vector product, we know that B cross C is nothing but minus C cross B. So, that is why A dot B cross C is same as minus A dot C cross B. We can interchange, thus we can say A comma B comma C is nothing but minus B comma C comma A. So these are some of the properties of scalar triple product. Now prove that vector A comma vector B comma vector C plus D is equal to ABC ABD. So first let us take this. So we have vector A comma vector B comma vector C plus vector D. See, ABC is nothing but A dot B cross C. So like this we will write the given. So we can write this as vector A dot vector B cross C plus D. So this is A dot, let us multiply, this becomes B cross C plus B cross D. Now let us multiply A inside, A dot B cross C plus A dot B cross D. Again let us write this in the box product form. So then A dot B cross C can be written as vector A comma vector B vector C in box, and here this becomes vector A comma vector B comma vector D. Hence we have proved. So these are very simple 2 mark or 3 mark questions from scalar triple product. Next, prove that vector A plus vector B comma vector B plus vector C comma vector C plus vector A is 2 times the box product A, B, C. So first let us write this in terms of scalar triple product. So how I can write this? I can write it as A plus B dot B plus C cross C plus E. Now this A plus B, keep it outside. Let us multiply inside. So we have B cross C plus B cross A plus C cross C plus C cross A. We know that C cross C is 0. That is the vector product of the same vectors A cross A or B cross B is 0. So A cross A, B cross B, or it may be C cross C. So they are all equal to 0. Hence I can consider this is equal to 0. Next, here it becomes vector A plus vector B dot, we are left with B cross C plus B cross A. So here it is cross and plus C cross A. Now multiply vector A, then this becomes dot here. So A dot B cross C plus A dot B cross A plus A dot C cross A plus next we will multiply B here. So then it is B dot B cross C plus B dot B cross A plus B dot C cross A. Again from the property of scalar triple product, when the two vectors are same inside the scalar product, the value is 0. So for the first one, we have A dot B cross C. I can write this in terms of A comma B comma C. The second one is 0. Third one, we have A and A same here. So it is 0. Fourth one is also 0 because we have B dot B cross C. So we have two vectors same here, 0. So here it is 0 again. And the last one can be written as B comma C comma A. We know that the scalar triple product is cyclically arranged. So B comma C comma A is same as A comma B comma C. So therefore here A comma B comma C plus A comma B comma C, which is nothing but 2 times vector A comma vector B comma vector C. So that is the RHS. Hence we have proved. Next, so we have a geometrical application of scalar triple product. So where does it helps? The magnitude of scalar triple product. So that is the magnitude of this scalar triple product when you take, it is always denotes the volume of parallelepiped formed by adjacent side whose three vectors are vector A plus vector B, vector C. So parallelepiped is a solid whose face looks like a parallelogram here. So the face here looks like a parallelogram here. So I can say if this is one vector, this is another vector, and this is another vector. Consider this as vector A, vector B, and vector C. So if these are the three vectors which denotes the face of a parallelepiped, then the volume or the magnitude of this vector or whatever the scalar value you will get using scalar triple product, it always gives you the volume of this parallelepiped. Now how to find the volume or how to express these three vectors? Again in the determinant form. If you expand the determinant, you will get the volume of parallelepiped in cubic units. Next, coplanarity of three vectors. So when you say that the three vectors are on the same plane or they are called as coplanar, when it is possible, when the scalar triple product is 0. If you have three vectors, vector A, vector B and vector C. Let me consider vector A, vector B, vector C. If you consider all of them in one singular plane, then their scalar triple product must be equal to 0. So to show that the three vectors are coplanar, we can show that their scalar triple product is 0. Similarly, suppose if you have 4 points, so that you can form three vectors from the 4 points, then they are also said to be coplanar. Suppose if you have 4 points A, B, C, D, then the vectors from A to B, A to C and A to D, you can say this as vector AB, vector AC and vector AD. So they are also coplanar. Again, if their scalar triple product is 0, that is AB, AC, AD is equal to 0, or I can write vector AB dot vector AC cross AD is equal to 0. If the determinant value of these 4 points are 0, then we can say they are coplanar. The points lie on the same plane. Next, show that the 4 points with position vector 4i plus 8j plus 12k, 2i 4j plus 6k and 3i 5j plus 4k and 5i plus 8j plus 5k are coplanar. So here we have 4 points. Let me consider this as point A, B and this as point C and point D. So let me take what is AB and AC and AD. Their position vectors are given here. So just subtract the points. So AB means it is OB minus OA. So I'm just subtracting the points here. So OB minus OA means 2 minus 4 is minus 2, comma 4 minus 8 is minus 4, comma 6 minus 12 is minus 6. So I'm just writing only the vertices because for the determinants I need only the components. You can express it also in the form of minus 2i, minus 4j, minus 6k. Next, OC minus OA. I need to subtract vector C, vector A. So 3 minus 4 minus 1, comma 5 minus 8 minus 3, comma 4 minus 12 minus 8. Next, I'll take OD minus OA. So again I have 5 minus 4, 1, 8 minus 8, 0, 5 minus 12, minus 7. So these are the vertices. Now let us take the scalar triple product, that is AB, comma AC, comma AD. So that is, write the components in the determinant form. -2, -4, -6, -1, -3, -8, 1, 0, -7. So let us expand this. First is -2. So we have 3 sevens are 21, -0. Next we have minus of -4. So -4 again. We have 7 plus 8. Next we have -6 here. For -6 it is 0 plus 3. So -21 -2. So which becomes -42. Next we have 7, 8, 15. 15 fours are 60. Next we have -18. So -42 -18 is -60 plus 60. So which get cancelled? So 0. So thus we have got AB, comma AC and AD. Value is 0. So therefore A, comma B, comma C and D are coplanar. So just showing that their scalar triple product is 0, we can show that the 4 points are coplanar. Next, find x such that the 4 points A 3, 2, 1, B 4, x 5, C 4, 2, -2 and D 6, 5, -1 are coplanar. So we know that we can write vector AB, vector AC, vector AD is equal to 0 because given that the points are coplanar. Now to find AB here, so AB is nothing but OB minus OA. So vector AB is nothing but vector OB minus vector OA. So let's write down. So 4 minus 3, 1. Next we have x minus 2. Next we have 5 minus 1, 4. So these are the components of AB. Next we will take AC. OC minus OA. So what is C? We have 4 minus 3, 1, 2 minus 2, 0, minus 2 minus 1, minus 3. Next we have components of AD. OD minus OA. So we have 6 minus 3, 3, 5 minus 2, 3, minus 1, minus 1, minus 2. So now let's write down this. Let us use this equation we have. So AB, comma AC, comma AD is equal to 0. That is the box product or the scalar triple product is 0. That is the determinant of 1, x minus 2, 4, 1, 0, minus 3, 3, 3, minus 2 is equal to 0. So we will expand the determinant 1, 0 plus 9 minus x minus 2. Delete the column, delete the row. We have minus 2 plus 9 again. Next we will take plus 4. For 4 we have 3 minus 0 is equal to 0. So here we have 9 minus 2 plus 9 is 7. 7 into x is 7x. So next we have plus 7 2s are 14, 4 3s are 12 is equal to 0. So now here we have 9 plus 14 plus 12 which is 35 minus 7x is equal to 0, or I can write 7x is equal to 35. X is equal to 35 divided by 7. When you cancel, you will get the value of x as 5. So therefore the value of x is 5. Next question. Find lambda if vector A is equal to I plus 3j plus k, vector B is equal to 2i minus j minus 3k, and vector C is equal to lambda I plus 7j plus 3k are coplanar. If the three vectors are coplanar, their scalar triple product is 0. That is A dot B cross C is equal to 0. Now A dot B cross C can be written in the form of a determinant, that is the components of the three vectors 1, 3, 1. Next we have 2, minus 1, minus 3. Next we have lambda 7 and 3 is equal to 0. Now let us expand this determinant. It is 1 into minus 3 plus 20. Next we have minus 3. So delete the row column. 3 2s are 6. Minus 3 lambda becomes plus 3 lambda. Next we have minus 1. We have 7 2s are 14. Minus lambda becomes plus lambda is equal to 0. Here we have 18. Next we have 18 minus 9 lambda. Next we have minus 14 and this is plus 1, so plus 14. Again we have lambda is equal to 0. So 18 minus 18 cancels. Minus lambda, lambda is minus 8 lambda plus 14 is equal to 0. Or I can write 8 lambda is equal to 14. Lambda is equal to 14 divided by 8. Or I can write cancelling with 2. 2 7s are 14. 2 4s are 8. So therefore the value of lambda is 7 by 4. Next, for any three vectors a comma b comma c, prove that vector a minus b, vector b minus c and vector c minus a are coplanar. So to show that they are coplanar, we need to show that their box product or scalar triple product is 0. First let us consider the scalar triple product of these three vectors. Vector a minus vector b dot vector b minus vector c cross vector c minus vector a. Now leave it as it is, vector a minus vector b. So let us clear the cross product. We have b cross c minus b cross a. Next we have minus c cross c plus c cross a. So c cross c here, this will become 0 because the vector product of the same vectors is 0. Now let us multiply a with all these. Next we will take b. First we will multiply a dot b cross c minus a dot b cross a. This is 0 plus a dot c cross a. Next we will going to multiply minus b. So minus b dot b cross c. Minus into minus plus b dot b cross a. Minus into plus, which is minus b dot c cross a. So this is equal to a dot b cross c can be written in the form of box a comma b comma c. A dot b cross a, since the two vectors are same, the box product is 0. Here also it is 0 because two vectors are same. Two vectors are same, 0. Two vectors are same, 0. And this I can write it as b dot c cross a, that is b comma c comma a. We know that they are cyclic. So therefore I can write this as a comma b comma c minus b comma c comma a can also be written as a comma b comma c. So which get cancels. So therefore the value is equal to 0. Since the scalar triple product of these three vectors are 0, we can say that they are coplanar. Now coming to the scalar triple product, we have a dot b cross c as the scalar triple product whose values can be taken in the form of determinant a1, a2, a3, b1, b2, b3, c1, c2, c3. And the geometrical application of the scalar triple product is that to show that any three vectors are coplanar or any 4 points are coplanar, we need to show that the value is equal to 0. If the scalar triple product of vector A, B, C is 0, then means the 3 vectors are coplanar. When any 4 points are given, convert it into 3 vectors and show that they are coplanar. And also, always A dot B cross C represents the volume of parallelopiped. The value always gives you the volume of a parallelepiped, which is a solid whose face looks like a parallelogram. This is all about your chapter vectors. The dot product, vector product and scalar triple product are the most important concepts to study. We'll meet you in the next session with a new chapter. Until then, keep watching, keep learning, keep exploring. Thank you.